Okay, now we can start our first formal topic, that is potential energy surface. Now, what is a potential energy surface? To understand this topic, you need to know that there are two things which are connected to one another. One is structure and the other one is energy. So the structure-energy relationship is going to deliver potential energy surface, and that is fundamental to computational chemistry. The potential energy surface describes the relationship between energy and structure. Now, before I give you explanation of potential energy surface, let me tell you that potential energy surface is calculated at 0 Kelvin. Now, why it is calculated at 0 Kelvin? There is one fundamental point that the actual energy of a system is a combination of kinetic energy and potential energy. Kinetic energy depends on momenta, whereas potential energy depends on coordinates. Now, the kinetic energy depends on momenta and potential energy depends on coordinates. At 0 Kelvin, the kinetic energy of the system should be 0. So the total energy is equal to potential energy of the system. Now, the energy calculation method provides access to potential energy surface. And in molecular mechanics, the energy of the system is depending on bond stretching term, angle bending term, plus some torsional terms. For the time being, don't worry about these equations because in a later section when we will talk about molecular mechanics, we will see all these equations, how they are built, and what are the meanings of each equation. This will come later. For the time being, just try to understand that the energy of the system is depending on bond lengths, bond angles, torsional angles, and so on. In quantum mechanics, the energy depends on the Hamiltonian operator. Now, in Schrödinger equation, we know that this operator, function of nuclear coordinates, gives you energy of the system. Now, whatever the case is, whether it's molecular mechanics or quantum mechanics, these methods give energy of a single nuclear configuration. You can see here, now energy here is depending on Ri. So bear in mind in these lectures, whenever capital R is written, it means the coordinates of nuclei. When small r is written, it is the coordinates of electron. Now in this case, the energy is depending on the nuclei coordinates. Same is the case here, energy is function of nuclei coordinates. So for a specific set of coordinates for nuclei, it has a specific energy. So you can see here, these methods give the energy of a single nuclear configuration. We have to do a lot of calculations to construct an entire potential energy surface. Now, you might be thinking about that this might be something really complicated, but honestly speaking, you might have seen the potential energy surface in your high school. Let's have a look at this diagram here. In your high school textbook chemistry, you have seen the example of hydrogen molecule, that when two hydrogen atoms are really far apart, they are not interacting with one another, the energy of the system is quite high. But as soon as you start bringing them close together, a point will come that they make a bond, and if you try to further push them together, the energy of the system rises sharply. Now on this x-axis, we have the distance between two atoms. Now in this case, we have the example of nitrogen. In nitrogen, what we are scanning here is nitrogen-nitrogen bond distance. Now this is one of the simplest potential energy surface diagram because it involves two atoms. For two atoms, we have only one variable, and that is nitrogen-nitrogen bond distance. Similarly, if you take the example of H2, in that case, the variable will be hydrogen-hydrogen bond distance. For complicated molecules, the number of variables increase and the potential energy surface also starts becoming quite complicated. But for diatomic molecule, we have one variable, and that is the distance between two atoms which are bonded together. Let's say if we place them really far apart, for example, in this case, starting from 7 angstrom, it means that two nitrogen atoms are placed 7 angstrom apart. Now, you are going to bring them close gradually with a step size of 0.2 angstrom. You can see that the energy of the system starts decreasing slowly at the beginning, but beyond, or once you reach at 3 angstrom and try to decrease it further, the energy of the system now starts decreasing a bit rapidly. It comes to a minimum point around 1 angstrom, and then it starts increasing rapidly. Now, what you can see here, the energy of the system is decreasing, and the lowest energy structure is seen around 1 angstrom, because on y-axis we have the energy of the system. Now, at 1 angstrom, we see that the structure is of the lowest energy, and we can assume, or we can say, that a bond is formed between two nitrogen atoms. Now, to construct this diagram, how many points have been calculated, starting from 7 angstrom going up to almost like 0.5. So between 7 and 0.5 angstrom, taking a step size of 0.2 angstrom, these are 34 steps. So you can see, to construct this diagram, 30 plus points are taken, and the energy is calculated for each point. So you calculate energy at several distinct values of D and N, and it's called as potential energy surface scan. Now you interpolate between points to construct PES. You are taking points, plotting their energy, and now you're interpolating them, and you can construct a potential energy surface diagram. So it gives relevant structural and energetic information. Now you can see here, for any point, you know the distance between those atoms, and you can know the energy associated with it. So such type of diagram where energy is related to geometric parameters is called as potential energy surface diagram. Now the question arises, what is the dimensionality of potential energy surface? How many dimensions are there? In principle, for any atom in a molecule, it has 3 degrees of freedom. So let's say if you have N2 molecule, with N2 molecule, you have 3n degrees of freedom. Now in this case, there are 2 atoms, so 3 into 2 is equal to 6. So now for nitrogen molecule, there are 6 degrees of freedom. 3 of them are translation of nitrogen molecule as a whole along x-axis, nitrogen molecule translation along y-axis, and a nitrogen molecule translation along z-axis. These are 3 translational degrees of freedom. Now for a linear molecule, there are 2 degrees of freedom for rotation. And the remaining last one is the degree of freedom for vibration, or the degree of freedom for potential energy surface diagram. For a linear molecule, no matter how much you can do, you can never change it from linear to some nonlinear structure. A diatomic molecule will always stay as a linear molecule. So that's why it has only 1 degree of freedom for potential energy surface. But for molecules bigger than diatomic, it has 3n minus 6 degrees of freedom. Now the question arises, why does the translation not change the energy of the system? You can see here, let's say if you take a diatomic molecule in certain area, whether you place the diatomic molecule at this position, or this position, as long as the distance between these two atoms is constant, it's not changing in all these three diagrams, the energy of the system will stay the same. So it means translation does not change the energy of the system. Similarly, if you rotate the molecule, rotation also does not change the energy of the system. So potential energy does not depend on the absolute location of the atoms, but on their relative position. Now these three figures, they show that this diatomic molecule has different absolute position. In this corner, somewhere here, and on this corner, they have their different absolute position. But the relative position of one atom to the other one is same here, and same here. Despite being different absolute position, their relative positions are same, so the potential energy is same. So potential energy does not depend on the absolute location of the atoms, but on the relative position, and that is the molecular geometry. So a typical potential energy surface has the same dimensionality as the number of geometric degrees of freedom. So as I mentioned earlier, that for a triatomic molecule or even larger one, you have 3n-6 degrees of freedom. You might have seen this number in vibrational spectroscopy, where we talk about vibrational degrees of freedom. Now, in this case, in potential energy surface, this number is slightly different than the number that you see in vibrational spectroscopy. How it is different? Let's say if we take the example of carbon dioxide. Carbon dioxide is a linear molecule. According to vibrational degree of freedom, it has 4 degrees of freedom according to the rule of 3n-5. But for potential energy surface, we will apply the rule of 3n-6 because once we change certain parameters, we can get to 3n-6. We'll see with an example later. Let's move on to the triatomic molecule, which is relatively simple, and that is the example of ozone to isoozone. Now you can see here, it is a triatomic molecule, but it has symmetry. O1, O2, O1, O2. These two bond lengths are similar. Now in this case, in principle, there should be 3 degrees of freedom. If we apply the rule of 3n-6, there should be 3 degrees of freedom. But because of symmetry, one of them is lost. How it is lost, I can show you. First, you need to understand what are the 3 degrees of freedom. O1, O2, this bond length is 1 degree of freedom. This O1, O2 is the 2nd degree of freedom. And this angle here, O2, O1, O2 is the 3rd degree of freedom. Now out of these two, this one and this one, they are identical. So in principle or in nutshell, we are left with 2 degrees of freedom. And those 2 degrees of freedom are the bond length here and the bond angle here. And keep in mind, to construct a potential energy surface diagram, you need to have energy on one axis and the variables on the other axis. Now in the case of nitrogen example, we had only one variable, so we could plot it in 2-dimensional diagram. One variable is distance and the other one associated or dependent variable is energy. Now in the case of ozone, we have 2 independent variables, bond length and bond angle, and the third one dependent variable is energy. So we need to construct a potential energy surface diagram which is 3-dimensional. On one axis we have the distance O1, O2. On the second axis we plot the angle which is O2, O1, O2. And on the third axis we have energy And that's how we can construct a potential energy surface diagram. So we systematically vary this angle and this bond distance on a grid and calculate the energy at each set of values. So it requires a large number of calculations due to 2D nature of the system. Let's say going from 1.37 to 1.70, and let's say we're going to have like 8 points here, or maybe 9. And let's say on this side we go from 60 or 50 to 140 or 160 degree, and we can have 11 points here. So 11 into 9 is going to give us 99 points for structure calculation. So it means to construct this potential energy diagram where we have 11 values on this axis, 9 values on this axis, and then to construct this potential energy surface diagram, we need to have 99 points. And this complexity can further increase if you decrease the step size here and if you decrease the step size here. Let's say you make 40 points here or 40 steps here. In that case, to construct this diagram, you need 1600 calculation, 40 into 40. And if you further decrease the step size, maybe 50 into 50, then you can probably requiring 2500 calculations to construct this potential energy surface diagram. Or this is the case with 2 variables. And the situation can go even more complex if we have the number of variables even beyond 2.